W3B, so values, and find a way to map them to y hat. So you can imagine doing gradient descent so that these parameters W3, B3, as well as maybe W4, B4, and even W5, B5, maybe trying to learn those parameters so the network does a good job mapping from the values I drew in black on the left to the output values y hat. But now let's uncover the left of the network again. The network is also adapting parameters W2, B2, and W1, B1. And so as these parameters change, these values A2 will also change. So from the perspective of the third hidden layer, these hidden unit values are changing all the time, and so it's suffering from the problem of covariate shift that we talked about on the previous line. So what Batch norm does is it reduces the amount that the distribution of these hidden unit values shifts around. And if we were to plot the distribution of these hidden unit values, maybe this is, technically we normalize a z, so this is actually z21 and z22, and we're just going to plot two values instead of four values so we can visualize it in 2D. What Batch norm is saying is that the values for z21 and z22 can change, and indeed they will change when the neural network updates the parameter z. What Batch norm is saying is that the values for z21 and z22 can change, and indeed they will change when the neural network updates the parameters in the earlier layers. But what Batch norm ensures is that no matter how it changes, the mean and variance of z21 and z22 will remain the same. So even if the exact values of z21 and z22 change, their mean and variance will at least stay, say, mean 0 and variance 1. Or not necessarily mean 0 and variance 1, but whatever value is governed by beta 2 and gamma 2, which if the neural network chooses can force it to be mean 0 and variance 1, or really any other mean and variance. But what this does is it limits the amount to which updating the parameters in the earlier layers can affect the distribution of values that the third layer now sees and therefore has to learn on. And so Batch norm reduces the problem of the input values changing. It really causes these values of the input values changing. It really causes these values to become more stable so that the later layers of the neural network has more firm ground to stand on. And even though the input distribution changes a bit, it changes less. And what this does is, even as the earlier layers keep learning, the amount that this forces the later layers to adapt to its earlier layers changes is reduced. Or if you will, it weakens the coupling between what the earlier layers parameters has to do and what the later layers parameters have to do. And so it allows each layer of the network to learn by itself, a little bit more independently of other layers. And this has the effect of speeding up learning in the whole network. So I hope this gives some better intuition, but the takeaway is that Batch norm means that, especially from the perspective of one of the layers, more independently of other layers, and this has the effect of speeding up learning in the whole network. So I hope this gives some better intuition, but the takeaway is that Batch norm means that, especially from the perspective of one of the layers, later layers of the neural network, the earlier layers don't get to shift around as much because they're constrained to have the same mean and variance. And so this makes the job of learning in the later layers easier. It turns out Batch norm has a second effect. It has a slight regularization effect. So one non-intuitive thing of a batch norm is that each mini batch, say mini batch xt, has the value is zt has the values zl scaled by the mean and variance computed on just that one mini batch. Now, because the mean and variance computed on just that mini batch, as opposed to computed on the entire data set, that mean and variance has a little bit of noise to compute it on the entire data set. That mean and variance has a little bit of noise in it because it's computed just on your mini batch of, say, 64 or 128 or maybe 256 or larger training samples. So because the mean and variance is a little bit noisy because it's estimated just a relative. To the small sample of data, the scaling process going from ZL to Z tilde L, that process is a little bit noisy as well because it's computed using a slightly noisy mean and variance. So, similar to dropout, it adds some noise to each hidden layer's activations. The way dropout adds noise is it takes the hidden units and it multiplies it by 0 with some probability and multiplies it by 1 with some probability. And so dropout adds multiplicative noise because it's multiplied by 0 or 1. Whereas batch norm has multiplicative noise because it's scaling by the standard deviation, as well as additive noise because it's subtracting the mean. Where here, the estimates of the mean and the standard deviation are noisy. And so similar to mean and the standard deviation are noisy. And so similar to dropout, batch norm therefore has a slight regularization effect. Because by adding noise to the hidden units, it's forcing the downstream hidden units not to rely too much on any one hidden unit. And so similar to dropout, this adds noise to hidden layers and therefore has a very slight regularization effect. Because the noise added is quite small, this is not a huge regularization effect, and you might choose to use batch norm together with dropout, and you might use batch norm together with dropout if you want the more powerful regularization effect of dropout. And maybe one other slightly non-intuitive effect is that if you use a bigger mini batch size, right? So if you use a mini batch size of say 512 instead of 64, by using a larger mini batch size, you're reducing this noise and therefore also reducing this regularization effect. Size, you're reducing this noise and therefore also reducing this regularization effect. So that's one strange property of dropout, which is that by using a bigger mini batch size, you reduce the regularization effect. Having said this, I wouldn't really use batch norm as a regularizer. That's really not the intent of batch norm, but sometimes it has this extra intended or unintended effect on your learning algorithm. But really, don't turn to batch norm as a regularization. Use it as a way to normalize your hidden units activations and therefore speed up learning. And I think the regularization is an almost unintimidations and therefore speed up learning. And I think the normal, but really don't turn to Batch norm as a regularization. Use it as a way to normalize your hidden units, activations, and therefore speed up learning. And I think the regularization is an almost unintended side effect. So I hope that gives you better intuition about what Batch norm is doing. Before we wrap up the discussion on Batch norm, there's one more detail I want to make sure you know, which is that Batch norm handles data one mini batch at a time. It computes mean and variances on mini batches. So at test time, you're trying to make predictions, trying to evaluate the neural network. You might not have a mini batch of examples. You might be processing one single example at a time. So at test time, you need to do something slightly differently to make sure your predictions make sense. That in the next and final video on Batch norm, let's talk over the details of what you need to do in order to take your neural network trained using Batch norm to make predictions. Batch norm processes your data one mini batch at a time. But at test time, you might need to process the examples one at a time. Let's see how you can adapt your network to do that. Recall that during training, here are the equations you'd use. Implement batch norm. Within a single mini batch, you sum over that mini batch of the zi values to compute the mean. So here, you're just summing over the examples in the z. Within a drills one at a time. Let's see how you can adapt your network to do that. Recall that during training, here are the equations you'd use to implement batch norm. Within a single mini batch, you sum over that mini batch of the zi values to compute the mean. So here are the batches you'd use to implement batch norm. Within a single mini batch, you sum over that mini batch of the zi values to compute the mean. So here, you're just summing over the examples in one. the number of examples in the mini batch, not in the whole training set. Then you compute the variance, and then you compute z norm by scaling by the mean and standard deviation with epsilon added for numerical stability, and then z tilde is taking z norm and rescaling by gamma and beta. So notice that mu and sigma squared, which you need for this scaling calculation, are computed on the entire mini batch. But at test time, you might not have a mini batch of 64, 128, or 256 examples to process at the same time. So you need some different way of coming up with mu and sigma squared. And if you have just one example, taking the mean and variance of that one example doesn't make sense. So what's actually done in order to apply your neural network at test time is to come up with some separate estimate of mu and sigma squared. And in typical implementations of batch norm, what you do is estimate this using a exponentially weighted average, where the average is across the mini batches. So to be very concrete, here's what I mean. Let's pick some layer L, and let's say you're going through mini batches x1, x2, together with the corresponding values of y, and so on. So when training on x1, for that layer L, you get some mu L, and in fact, I'm going to write this as mu for the first mini batch and that layer. And then when you train on the second mini batch, for that layer and that mini batch, you end up with some second value of mu. And then for the third mini batch, in this hidden layer, you end up with some third value for mu. So just as we saw how to use an exponentially weighted average to compute the mean of theta 1, theta 2, theta 3 when you were trying to compute a exponentially weighted average of the current temperature, you would do that to keep track of sort of what's the latest average value of this mean vector you've seen. So that exponentially weighted average becomes your estimate for what the mean of the z's is for that hidden layer. And similarly, you use an exponentially weighted average to keep track of these values of sigma squared that you see on the first mini batch in that layer, sigma squared that you see on the second mini batch, and so on. So you keep a running average of the mu and the sigma squared that you're seeing for each layer as you train the neural network across different mini batches. Then finally, at test time, what you do is, in place of this equation, you would just compute z norm using whatever value z you have and using your exponentially weighted average of the mu and sigma squared, whatever was the latest value you have, to do the scaling here. And then you would compute z tilde on your one test example using that z norm that we just computed on the left, and using the beta and gamma parameters that you had learned during your neural network training process. So the takeaway from this is that during training time, mu and sigma squared are computed on an entire mini batch of, say 64, 128, or some number of examples. But at test time, you might need to process a single example at a time. So the way to do that is to estimate mu and sigma squared from your training set. And there are many ways to do that. You could, in theory, run your whole training set through your final network to get mu and sigma squared. But in practice, what people usually do is implement an exponentially weighted average, where you just keep track of the mu and sigma squared values you're seeing during training, and use an exponentially weighted average, also sometimes called a running average, to just get a rough estimate of mu and sigma squared. And then you use those values of mu and sigma squared at test time to do the scaling you need of the hidden unit values z. In practice, this process is pretty robust to the exact way you use to estimate mu and sigma squared. So I wouldn't worry too much about exactly how you do this. And if you're using a deep learning framework, they'll usually have some default way to estimate the mu and sigma squared that should work reasonably well as well. But in practice, any reasonable way to estimate the mean and variance of your hidden unit values z should work fine at test. So that's it for dash norm, and using it, I think you'll be able to train much deeper networks and get your learning algorithm to run much more quickly. Before we wrap up for this week, I want to share with you some thoughts on deep learning frameworks as well. Let's start to talk about that in the next video. So far, the classification examples we talked about have used binary classification where you had two possible labels, 0 or 1. Is it a cat or is it not a cat? What if you have multiple possible classes? There's a generalization of logistic regression called softmax regression that lets you make predictions where you're trying to recognize one of C or one of multiple classes rather than just recognize two classes. Let's take a look. Let's say that instead of just recognizing cats, you want to recognize cats, dogs, and baby chicks. So I'm going to call cats class 1, dogs class 2, baby chicks class 3, and if none of the above, then there's an other or none of the above class, which I'm going to call class 0. So here's an example of the images and the classes they belong to. That's a picture of a baby chick, so the class is 3, cat is class 1, dog is class 2. That's a, I guess that's a koala, so that's a none of the above, so that's class 0, class 3, and so on. So the notation we're going to use is, I'm going to use capital C to denote the number of classes you're trying to categorize your inputs into, and in this case, you have 4 possible classes, including the other or the none of the above class. So when you have 4 classes, the numbers indexing your classes would be 0 through C minus 1, through capital C minus 1. So in other words, it would be 0, 1, 2, or 3. In this case, we're going to build a neural network where the output layer has 4, or in this case, the variable capital alphabet C output units. So n, the number of units in the output layer, which is layer L, is going to be equal to 4, or more generally, is going to be equal to C. And what we want is for the number of units in the output layer to tell us what is the probability of each of these 4 classes. So the first node here is this output, and we want it to output the probability that is the other class given the input x. This will output probability cat, given x. This will output probability that is a dog, given x. That will output the probability. I'm just going to abbreviate baby chick to be BC. So probably of a baby chick, abbreviated BC, given the input x. So here, the output labels y hat is going to be a 4 by 1 dimensional vector because it now has to output 4 numbers, giving you these 4 probabilities. And because probabilities should sum to 1, the 4 numbers in the output y hat, they should sum to 1. The standard model for getting a neural network to do this uses what's called a softmax layer in the output layer in order to generate these outputs. Let me write down the math and we can come back and get some intuition about what the softmax layer is doing. So in the final layer of the neural network, you are going to compute as usual the linear part of the layer. So z capital L, that's the z variable for the final layer. So remember, this is layer capital L. So as usual, you compute that as WL times the activation of the previous layer plus the biases for that final layer. Now, having computed z, you now need to apply what's called the softmax activation function. So the activation function is a bit unusual for the softmax layer, but this is what it does. First, we're going to compute a temporary variable, which we call t, which is e to the zl. So this is applied element-wise. So zl here, in our example, zl is going to be 4 by 1. It's a 4-dimensional vector. So t itself, e to the zl, that's an element-wise exponentiation. T will also be a 4 by 1 dimensional vector. Then the output, al, is going to be basically the vector t but normalized to sum to 1. So al is going to be e to the zl divided by sum from j equals 1 through 4, because we have 4 classes of t subscript I. So another way of saying this is that al is also a 4 by 1 vector, and the ith element of this 4-dimensional vector, let's write down al subscript I, this is going to be equal to ti over sum of ti. Okay. In case this math isn't clear, we'll do an example in a minute that'll make this clearer. So in case this math isn't clear, let's go through a specific example that will make this clearer. Let's say that you've computed ZL, and ZL is a 4-dimensional vector. Let's say it's 5, 2, negative 1, 3. What we're going to do is use this element-wise exponentiation to compute this vector t. So t is going to be e to the 5, e to the 2, e to the negative 5, e to the 3. And if you plug that into a calculator, these are the values you get. E to the 5 is 148.4. E squared is about 7.4. E to the negative 1 is 0.4. And E cubed is 20.1. And so the way we go from the vector t to the vector al is to just normalize these entries to sum to 1. So if you sum up the elements of t, if you just add up those 4 numbers, you get 176.3. So finally, al is just going to be this vector t as a vector divided by 176.3. So for example, this first node here, this will output e to the 5 divided by 176.3, and that turns out to be 0.842. So saying that for this image, if this is the value of z you get, the chance of it being class 0 is 84.2%. And then the next node outputs e squared over 176.3. That turns out to be 0.042, so it's 4.2% chance. The next one is e to the negative 1 over that, which is 4.42. And the final one is e cubed over that, which is 0.114. So about an 11.4% chance that this is class number 3, which I guess is the Lagrangian class. So there's a chance of it being class 0, class 1, class 2, class 3. So the output of the neural network, AL, this is also y hat. This is a 4 by 1 vector where the elements of this 4 by 1 vector are going to be these four numbers that we just computed. So this algorithm takes the vector ZL and maps it to four probabilities that sum to 1. And if we summarize what we just did to map from ZL to AL, this whole computation, computing the exponentiation to get this temporary variable t, and then normalizing, we can summarize this into a softmax activation function and say AL equals the activation function g applied to the vector ZL. The unusual thing about this particular activation function is that this activation function g, it takes as input a 4x1 vector and it outputs a 4x1 vector. So previously, our activation functions used to take in a single real value input. So for example, the sigmoid and the value activation functions input a real number and output a real number. The unusual thing about the softmax activation function is because it needs to normalize across the different possible outputs, it needs to take in a vector of inputs and then outputs a vector. So what are the things that a softmax classifier can represent? I'm going to show you some examples where you have inputs x1, x2, and these feed directly to a softmax layer that has 3 or 4 or more output nodes that then outputs y-hat. So I'm going to show you a neural network with no hidden layer, and all it does is compute z1 equals w1 times the input x plus b, and then the output a1 or y-hat is just the softmax activation function applied to z1. So in this neural network with no hidden layer, it should give you a sense of the types of things a softmax function can represent. So here's one example with just raw inputs x1 and x2, a softmax c equals 3 output causes can represent this type of decision boundary. Notice it's kind of a several linear decision boundaries, and this allows it to separate out the data into 3 classes. And in this diagram, what we did was we actually took the training set, just kind of shown in this figure, and trained the classifiers, and trained the softmax classifier with 3 output labels on the data, and then the color on this plot shows thresholding the outputs of the softmax classifier, and coloring in the input based on which one of the 3 outputs had the highest probability. So you can maybe kind of see that this is like a generalization of logistic regression with sort of linear decision boundaries, but with more than 2 classes, with instead of the classes being just 0, 1, the classes could be 0, 1, or 2. Here's another example of the decision boundary that a softmax classifier can represent when training a data set with 3 classes. And here's another one, right? So this is, but one intuition is that the decision boundary between any 2 classes will be linear. That's why you see, for example, the decision boundary between the yellow and the red classes, that's like a linear boundary. Between purple and red is not a linear decision boundary. Between purple and yellow is another linear decision boundary. But is able to use these different linear functions in order to separate the space into 3 classes. Let's look at some examples with more classes. So this example with c equals 4, so that the green class and softmax can continue to represent these types of linear decision boundaries between multiple classes. So here's one more example with c equals 5 classes, and here's one last example with c equals 6. So this shows the type of things a softmax classifier can do when there is no hidden layer. Of course, you have a much deeper neural network with x, and then some hidden units, more hidden units, and so on. Then you could learn even more complex nonlinear decision boundaries to separate out multiple different classes. So I hope this gives you a sense of what a softmax layer, what a softmax activation function in a neural network can do. In the next video, in the last video, you learned about the softmax layer and the softmax activation function. In this video, you deepen your understanding of softmax classification and also learn how to train a model that uses a softmax layer. Recall our earlier example where the output layer computes ZL as follows. So we have 4 classes, c equals 4, then ZL is going to be 4 by 1 dimensional vector, and we said we compute compute t, which is this temporary variable that performs element-wise exponentiation. And then finally, if the activation function for your output layer, g of L, is the softmax activation function, then the output will be this. It's basically taking that temporary variable t and normalizing it to sum to 1. So this then becomes A of L. So you notice that in the z vector, the biggest element is 5, and the biggest probability ends up being this first probability. The name softmax comes from contrasting it to what's called a hard max, which would have taken the vector z and mapped it to this vector. So hard max function will look at the elements of z and just put a 1 in the position of the biggest element of z, and then zeros everywhere else. And so this is a very hard max where the biggest element gets an output of 1 and everything else gets an output of 0. Whereas in contrast, the softmax is a more gentle mapping from z to these probabilities. So I'm not sure if this is a great name, but at least that was the intuition behind why we call it a softmax. It's in contrast to the hard max. And one thing I didn't really show, but had alluded to, is that in the early days of deep learning, people used to worry a lot about the optimization algorithm getting stuck in bad local optima. But as the theory of deep learning has advanced, our understanding of local optima is also changing. Let me show you how we now think about local optima and problems with the optimization problem in deep learning. So this was a picture people used to have in mind when they worried about local optima. Maybe you're trying to optimize some set of parameters, we call them W1 and W2, and the height of the surface is the cost function. So in this picture, it looks like there are a lot of local optima, in all those places, and it'd be easy for gradient descent or one of the other algorithms to get stuck on a local optimum rather than find its way to a global optimum. It turns out that if you're plotting a figure like this in 2 dimensions, then it's easy to create plots like this with a lot of different local optima.